as a preferred point about which the torque must be calculated. So let's do some few more basic questions. So we have a wall and then we have a maybe some sort of plank or rod or whatever you can imagine, and this thoroughly hinge here. This end cannot move, so this is kind of hinge. We can imagine there are two forces acting here, Rx and Ry. So whenever we have hinge, we always think of two force, not one force. And the other force will be gravity, which must be acting at the center mass. So for uniform rod or something like this, we can say gravity is here. Now imagine this angle is theta. So or take this angle is theta, and there is a string which is tied to the rod at a point which is L by 4. The length of the rod is L. Now the question is how much tension will develop in this string. So now the question is asking tension in the string. So definitely we have nothing to do with the what is the hinge force. Now if you try to solve by the laws of motion by just balancing the force, what you can write? You can write T must be equals to Rx and Ry must be equals to mg. So now this cannot solve the question because we don't know anything about the Rx. Okay. So it means we need torque equation anyway. And fortunately, the torque equation about the hinge directly gives the answer. So if you write the torque about the hinge, what we can write? So torque about O equals to what we can write? So T into 3L by 4 cos theta. This is the torque. And gravity will have the value mg into L by 2 sin theta. And because these are opposite in the sense, we can just write with sign convention. So this is plus and this is minus. And this gives you the answer mg So these kinds of questions are very common, and you can imagine this is like a less than J means level question. And now because you know the tension, sometimes they may ask you what is the hinge direction. So now the laws of motion will give you the hinge direction, and now Rx is equals to mg by 3 tan theta. And what about the Ry? So it is a question. Ry is anyway known to you. That's it. So questions like this will come. You need to be prepared. So you might have seen that in a game of lawn tennis, there is a referee, and the referee used to stand near the middle, near the net, you can say, with something like this. So it was like a sitting chair, and then two support. So instead of this, let me just hang a mask. Not hang a mask. Let's say,
This is the HC1 question, right?
yeah. Okay. Have you done this question?
Yes, sir.
Okay. So then we can leave this question. So what do we do here? Tell me.
Sir, we draw the FBD, and then there will be normal forces from both the point of contact at the bottom.
Correct.
Normal forces upward, so we equate mg is equal to 2n. Uh, so therefore, we will get the n value. They had asked the n value and the tension value. Uh,
Hmm.
yeah, sir.
And then tension value is how much? What is the tension value? So to get this is the center of the rod. Tell me the tension. If you have done this, then just tell me the tension quickly. So to get the tension value, what will you do? Tell me, guys.
So the torque will be developed by it will be like T L by 2 sine theta uh, for both of them.
Tell me how from like about which point you're getting the torque.
So from the
The
top,
greater than. Why? So why you thought of taking the torque about the topmost point? What was your logic?
so because it is not uh, because the tension is holding up so that the topmost point is not falling down.
Arthur? Because it's a symmetrical body. So for symmetrical body, we cannot write the torque about for the entire body. So first we need to cut the body. So once you cut it, what you're left with is a single rod, and because the two rods together are holding the mass, so the individually it is not holding the same mass. So all the hinge direction or the You can see the unknown force will develop here. So we have the hinge. This is like a hinge again, which we don't know anything about. This is the tension, and this is the normal. Now, if you draw the normal here, so this normal will definitely balance the mg. So in a way, the normal is known to us because this normal is known to us. It's a known value. This is the unknown value. This is the unknown value. So I can remove the one unknown by taking the hinge here as a point of interest, and then we just write the answer. And this is g into L by 2 sin theta, and this will be equals to n into L cos theta. The tension turns out to be 2 cot theta, 2n cot theta, and the n is mg by 2, obviously mg cot theta, right? So this was the logic. So let's do some more problem. So imagine we have a hemisphere and this solid hemisphere is kept on the floor. So definitely if I release this, it will slip, right? So assuming friction is sufficient, so we have enough friction to prevent the slipping. So to keep it vertical, to keep the base of the hemisphere vertical, we apply some pull force here. We apply some force here, F, and the radius of this hemisphere is R, and mass is A. So how much force you need to apply to keep it vertical? Assume friction is sufficient to prevent a slipping. So friction will do its job. So you need not to worry about friction at least. Okay. Is this clear? I hope the question is clear to all of you guys. Am I audible?
Yes, sir. So just one
Are-
question.
Pardon?
So I have one question. Sir, this is hollow.
Sorry.
Sorry.
So you can clearly see the unknown location is the bottom. Now, in fact, we can say that numerically what we can say is that F equals to Fs, like apply the laws of motion, and N equals to M. So this is what you can say. That is for sure. But Fs is not known to us. So there are many ways to solve this. You can find the torque about the center mass or find the torque about the hinge point. But finding the torque about the bottom will have the best effect because it will take away the torque of two forces, Fs and N, which will make things easier for us. So you can just write as torque about O equals to 0 because we are doing the equilibrium problem. And then the only torque we have to write is F and mg. So F into 2R is mg into 3R by 8. Correct. So F turns out to be 3 mg by 6. And now you know this is also equal to the friction force value, which was earlier unknown. And yeah, normal was anyway known. So you can find the answer like this. So when we have a body which is at equilibrium, then torque is the only way to move forward. So you may write the laws of motion or the the translational equilibrium condition, but you will realize that okay, that is not going to give you the answer which you're looking for, and therefore you need to think about which point we must take the torque to make this possible. So maybe I will take two more problem before I end this. So now you can repeat this question for the hollow sphere. You can repeat the question for the semicircular disc, maybe semicircular ring, and so on. It's all about finding the torque. That's it. So imagine if we have a room in which this is difficult to do, but anyway. This is again solid hemisphere. Let's say of radius r, mass m, and again the angle made by this line is theta, and the coefficient of friction is enormous between the floor and the hemisphere, but friction is zero here at this particular location. So there is no friction acting here, but the coefficient of friction here is mu zero. Okay. So now the question is, as the theta will decrease at one point, after one point it will start slipping. So you can keep it at rest only for some large theta. The question: what is the minimum angle for which the body will be at equilibrium? Question is fine. Or in fact, no, this is other way around. Let's make the question other way around. Let's say theta is given to you, and now we have to find the mu s. To find the minimum value of mu is to keep the body at rest. There. So I hope the question is clear. So if you want, you can try for a while, maybe 2 minutes, something else. Okay, so let me do this question now. So you need to draw the ABD first. So ABD is pretty much straightforward. So it's in one, and the tendency to slip left. So we can write as mu s n one. Now I can write mu s n one directly. Why? Because we're taking the limiting case itself. Because I'm saying what's the minimum value of mu s which can make this possible. So it means the friction must be limiting friction. So we can write it. Now the top is having no friction, so the only force will be normal. And I had already drawn this the line which is passing through the center, and so we were knowing that all the normal will pass through the center. Now gravity will act exactly at center mass. So we don't know from the concept of center mass it will act at a distance of 3 r by 8 from the base, as we know. Mg is acting here. And now there is a little bit of geometry. This is 9 theta. This is 90. This is 91 theta. So this is again theta. So now our job is done. We can write. Now what we can do is the best point to solve this question will be. So you can see that laws of motion. So if you write the laws of motion, then n2 is equals to uh, n2 is equals to mu s n1. The first question, and n1 is equals to m. I think that's the only first. Yeah. So in a way, we know all values. So n2 is how much? Mu s m. But the question is, we are looking for mu s itself. So we are trying to calculate the mu s. So we need to take some torque. So now the best point to calculate the torque is the C point. Why? Because N1 into passes to C. So the torque of N1 into about C will be 0. So putting the torque about C equals to 0 will give you the desired result. Although you can choose any other point, you can take bottom also, you can take the wall point also. But this is the best choice. So now what you can say that the torque about C due to the friction will be mu s N1 into R, because that's exactly our distance away. And this must be equals to mg multiplied by 3r by 8 sine theta. And the n1 is itself is mg. So you can, if you remember that n1 was mg, this cancels r cancels. So the mu s minimum we are deriving as 3 by 8 sine theta. So in general, is if I replace this by a hollow hemisphere and something, so the mu s minimum which you will get is ycm upon r into sine theta. You can substitute the formula in any body like this and you will get the answer. Okay, this is the one of the type of question which is very common. So you need to again know the center mass. You need to remember the center mass formula and solve the question. So what is the next question that we can do now? So we have two theorem actually, okay, which is very essential to solve some of the challenging questions in like very easy manner. So the first is called couple force, or simply couple. So what is couple? A pair. So if you have a body and if I just go some random line, so any body which experiences two equal and opposite force, equal in magnitude and opposite in direction. So now they are equal and opposite force. So couple means if a body experiences two equal and opposite force, we say this is a couple force. And the property of couple is something very distinct. Okay. So what is the property of couple force? It's very simple. The net force on a body is zero because the right and left will cancel out. So the left force is 0. That is one thing. And what about the right force? So left is 0 for sure. That's okay. So the net force is 0. Then is the net torque 0? Do you see the net torque is 0?
No, sir.
No. So let's say if I choose some random point at a center mass, and if I say this is x, and if I say this is a d minus x, so I'm taking the separation between the forces d. So what is the torque about the center mass? Both will add up because both will support it. So the upper force will try to tilt like this, and the lower will do the same. So in a way, they will support the torque. So the net will add up. So it is fx plus f of d minus x. And what is interesting that this answer will be how much? Only fd. In fact, no matter which point you choose on this line, anywhere else, the torque of a couple remains independent of the choice of the point. It is always equals to the force multiplied by the separation. So this is what you need to remember, that the torque is always equals to force, one of the force, like of course both are equal and opposite. So one of the force multiplied by their separation, the minimum separation. So once you know the minimum separation between the line of action of force, now if I draw a diagram like this, you should not get confused. So what is the couple force? What is the torque here? The torque is how much?
FD sin theta.
FD sin. Now, when the torque will be zero, what is the condition for torque to be zero? So the torque will be zero only when the D is zero. For torque equals to zero implies the D equals to zero because you cannot make F zero. So the only way we can make zero is when D is zero, which means if the line of action of two forces are collinear with each other. If a body is experiencing two forces which are collinear, if I draw the random body, and if the forces are collinear, then the torque will be zero for sure. So in case of couple force, the net force is anyway zero. So torque will be zero only when the forces are collinear, and together both it will bring the body at equilibrium. So the simple theorem is that if a body is only experiencing couple force, no other thing, no other forces, then for equilibrium of such body, the forces must be collinear. So if you want, you can put into literature. So for a body to be in equilibrium under the action of couple forces must be collinear. So only when the force is collinear, this could be possible. Understood? This is
Yes.
possible only for this case. For no other case, it is possible. Understood? And also, what we can say, something the point which I discussed as well. So torque due to couple only depends on separation between lines of action of not the, or you can say doesn't depend on point taken. Depends on axis taken. So no matter which axis you choose, you will get the same answer. Okay, so that is the idea of couple. So this is the one theorem. So if a body is experiencing only one force, the only way it can be in equilibrium is that the forces are collinear. So if that is the case, uh, that will actually take away the effort of calculating the torque. So you need not to actually do the torque calculation. If you know that only two forces are acting, there's no point in calculating torque at all. So this is the massless frame, and if it is a massless frame, then I mean, let's say this is L, this is A, this is B. So to keep this entire body at equilibrium, we are applying force at the this end. So how the force we must apply so that the entire frame remains at equilibrium. So what we know that the force that will develop near the hinge will be at the hinge. Okay, and the force you must apply here that must pass through the hinge. Then only it will be at equilibrium, right? Because the tail of the two force must be same. No?
Yes, sir.
If you apply force this way, and because the hinge is going to apply force for sure this way. Now this is the hinge net force, which is taking care of the x and y. So we call it R, and this is the force which you apply. Let's call it F. And if these two forces are collinear, then only this entire system will be at equilibrium, and therefore, without solving, you get the answer of the F value. So now we know the answer. If the F is the applied force, the hinge direction is how much? And you also know at what angle the force is applied with horizontal. So this is theta, so you correct tan theta equals to A by B. So they may ask you what is the theta and all. And see, we got the answer without solving anything because we know this is the case. Okay. So let's see something more. So now under the action of two force, things will be like this. And the two force generally comes in the chapter of electrostatics, where we have a dipole and electric field, uniform electric field. So the uniform electric field in the dipole always creates the couple force, because if you think of dipole having plus charge or minus charge, and if you keep in a uniform field, it will experience the QE here and the QE here. So this is the exactly example of couple force. And if I say this separation as L and the angle between the dipole moment vector. If you know the dipole moment vector is something like this, and the electric field is theta, then the torque about any point will be same. So we can just write the torque. Why? Because it's a couple force. So the couple, let's say this is the like a force F. So what is the torque? Now you know the torque. The torque will be
QE L sin theta.
exactly QL center. Now this is the torque, and no matter which point you choose, you will get the same answer. So you can choose this point, you can choose center mass, you can choose the other point, you can choose some other point, and that is why, by definition, if you remember that the charge multiplied by their separation we call dipole moment. So you will learn in class 12. This is called dipole moment, but you might have heard in chemistry.
Yes, sir.
So dipole moment is basically the charge magnitude, like, because both are equal and opposite charge. We take the charge magnitude and we multiply by their separation. We call it dipole moment. So that's a definition. And so the formula becomes Pe sin theta, where E is the electric field vector, and later on you can also write as Pe cross in vector notation. So if you want, and similarly we have the bar magnet with north pole and south pole, and if we imagine that they are kept in the uniform magnetic field B, and if the pole is strength, so there is something called pole strength. So earlier this used to be in the class 8 syllabus, but it is not now. So M is called the pole strength, and the magnetic force we write as M into B equivalent to what we write Q into E. This is like a force. And the pole strength is called the magnetic charge. So this is the equivalent of charge. So we call it a mag charge. And then again, this is the MB. And if I choose a separation as L, angle is theta. So it's the same answer. What you can say here? So the torque, the magnetic torque is how much? It is MBL sin theta, which is exactly the same answer. Just the way of writing will change. So the torque of magnetic force will be equals to ML B sin theta, which is we can write as PM, and the PM we write as M into B, and this becomes the magnetic torque. So couple forces are very much these two forces are which are very famous in class 12 physics. So there we need to find the torque, and it's very simple. So we may have a magnetic compass, and the compass is kept in the Earth's magnetic field. So the moment you put the compass in the field, the compass will experience the torque due to the magnetic field of Earth, and that's why it turns actually. And why it turns? To make the torque zero, and the only way it can make the torque zero is when it is collinear with what? So it is collinear with the electric
Field.
field or the field itself. So that is why every magnetic compass, if kept in the uniform magnetic field, it will align itself in the field itself. Then only the torque will be zero. Okay. So that is how we do the navigation. So the earlier pirates of Caribbean kind of thing. So they used to have a compass, and the compass works with the Earth's magnetic field. So they see how the compass is aligned by keeping it horizontal, and that's how they come to know that whether they are going towards the North Pole or South Pole or which direction. So in the vast ocean, looking at the direction is only possible with the help of compass, because you cannot see the signboard. So it's the ocean, you don't have the signboard there, and you can't see the land also. So you have no sense of direction there. So only the directional sense is the stars in the sky. So you need to be very good astronomer to understand the direction. Or if you're not a very good astronomer, then you have to depend on the compass. So compass was the biggest discovery because not everyone was good astronomer. So the earlier voyagers used to be very good astronomers. So they were knowing that exactly how to read the moon sign, sun sign, zodiac sign, whatever, constellation and all. Anyway, so your grandfather, I mean, if you would have asked them if they would have alive, they would have exactly they can predict the time by looking at the sky. Of course, the sky must be clear, not the polluted sky as of Mumbai, where it's difficult to see the sky at all, and Delhi is worst. Okay, so couple forces will have its own application in a variety of chapters, and just keep the eye open that you have to use this. So now this is even more important, and this is called equilibrium of bodies under the action of three forces. So what will be the condition that a body is at rest when three forces are acting? So we have just seen that if we have two forces, then
All
they must
should
be.
be 60 degree to each other.
So let's say we have three forces, F1 acting here, F2 acting here, F3 acting here. I mean, it could be anywhere. Let me make it like this. And I want to make sure that the body should be at rest because there are different values. And at the same time, the body should not rotate. So the torque must be zero and the net force must be zero. So the first thing first, for translational equilibrium, the net force must be zero. So now the question is how to make sure that the net torque is also zero. That is, the body is also at a rotational equilibrium. For rotational equilibrium, the condition is simple. So for rotational equilibrium, what we need to do? So the condition, the theorem says that for a body to be uh, in equilibrium under the action of three forces, the three forces must be concurrent. So this is the theorem. So for equilibrium, the three forces must be concurrent forces. Now, what does it mean? It means they must pass through the same point. So why this is so? Let's try to evaluate. Let's say we have only two forces acting on the body. So we can join these two forces by tail to tail by extending the line like this. So we can see that these two forces are, acting at this point. So their resultant will be somewhere between, correct? So they must have the resultant somewhere between. Now, if I extend this line of action of force, there is a trouble. The trouble is these two forces will have a resultant something like this, somewhere here and here. I can say this is F12, which is the resultant of 1 and 2. And the third force is, you can see, so I can remove that first two force by one single force. And then we have the third force and the first resultant, these two force. And we can say that these two are, of course, these two must be equal. Why these two must be equal? Because it is a translational equilibrium. It means the sum of any two force must be equal to the third force in value and opposite in direction. Do you realize this?
Yes,
So
sir.
for equilibrium, the for any two force if you add, it must be equal to the third force in numerical value and opposite in direction. So you can see here that F1 plus F2 must be minus F3. So the sum, this implies we can say F12, and if this is the case, it means first of all these two forces must be couple force. Now this is the wrong diagram, but imagine that this is true. So if we have two forces, F1, F2, and let's say their resultant is somewhere here. So just choose any. Now we know that for translational equilibrium, the third force must be opposite and equal, correct? So it could be like this. So it could be like this, or like this also. If I choose it not concurrent, if I choose somewhere else, what will happen? It will develop a couple. It will develop a torque actually. So the only way to prevent the torque is what? When this third force is exactly here. Understood? So when the third force is exactly here, which is like now making these three forces concurrent, then only the torque will be zero. And that is the exact reason that if a body is experiencing three forces, and if the body is at rest, the three force must be concurrent. Else, body cannot maintain the rotational equilibrium. It may have the translational, but not the rotational. So this is a very far-reaching consequence of this theorem, and you can use to solve a question of competition also. But you can also use this in your first semester of BTech, or maybe second semester. So let's do a problem to understand this concept in detail. So this is a very famous question from some Olympiad, Indian Olympiad, and there is a hemispherical ball, and then we have a stick which you release inside the ball, and the stick is massless, but the center mass of the stick is not at the center; it is somewhere. This is the stick. So let's say the center mass is somewhere here. So if the length is L, let's say this length is alpha L. Alpha could be any value, maybe 1/4, 1/3, or whatever. So I'm choosing this as alpha L. Okay. So now, if you slid this rod into the ball, what will happen? This rod will be something like this. So it will remain at equilibrium in this position, and we are assuming it's a frictionless surface. So now you may wonder why this is the shape. Now, if it is exactly uniform rod, then it will be exactly horizontal like this. Now, as I said, this is not uniform. Center mass is not at center, so it will be asymmetrically inside the ball at rest. So now try to understand why it is the case. So for that matter, we'll need to do the FBD. Let me first do the center of the ball because that's important to understand the FBD. And we all know the normal on a hemisphere will pass through the center because it's like a circle and property of circle. So join the end to the center, then only you can draw the FBD. And the normal will be passing to the center, right?
Yes, sir.
So now we know the two forces are very much known to us, N1 and N2. And you can also see that the N1 and N2 will intersect at C, the center of the ball. So now the obvious question is, the gravity will act at the center mass of the rod, and the gravity, let's say to mg here, the line of action, if it is something like this, it will never be at equilibrium because the three force must be concurrent to keep the body at equilibrium. And therefore, I will draw a vertical line because I know gravity is always vertical. And exactly at this point, the center mass must be there. This diagram is slightly offset, but this must be the center mass. So now we know the optimal location of center mass. And as per the diagram, we know this is alpha into L, which was unknown to us. Let's say the radius of this ball is R, and in fact we needed to solve anything. So the question was basically the question was, if I choose a the true center of the rod, the center means not center mass, center of the rod, the L by 2. If O is the L by 2 portion, the midpoint, and if I join this to the midpoint, may not look better, but okay, maybe something like this. So this is the midpoint, and you can see this is the midpoint. And if I draw a horizontal line, so my question was, what is this angle theta? It turns out to be this theta is exactly the same as this angle. And you can verify why. Because if you have a chord in a circle, now this is a property of circle. If you have a chord in a circle, then the chord and the radius will make a isosceles triangle, correct? And
Yes.
if you make it horizontal, the red line will be vertical, and as the rod will tilt, it will also tilt from vertical, correct? And both will tilt by same value. In fact, we can prove it. It's not a big deal. You can extend the line. This is 90 theta. This is 90 theta. This is 90. This is theta. So anyway, that's a simple idea. The actual question was, what is this angle theta? But to get this angle theta, we can just get this theta. And finding this theta is very easy because this is the vertical height h, which we know. The h is equal to how much? R square minus L square by 4, correct? Using the isosceles property of triangle. This is L by. So we are solving a geometrical problem instead of torque question. Although it's a torque problem that find the theta at which the rod will come to rest. Now you need to find the torque about some point C, and that's a very tedious job. So C will give you the torque zero due to the N1, N2 because it will pass through that. And then for mg, it must give you zero torque only, and that's why the only way it can happen is that mg is also passing through the C, correct? Because the first two forces giving zero answer, so the third must give the zero answer, no? Because alone you cannot balance by having non-zero torque. And now we are done. Why we are done? Because the alpha L is given to us, and this length we can find. What is this length? This will be how much? L by 2 minus alpha L, correct?
Yes.
So I'm assuming alpha is less than half, maybe 1/4, something like this. And therefore the tan theta is how much? Tan theta is L by 2 minus alpha L, correct? Upon H. So we got the answer as L 1 by 2 minus alpha upon R square minus L square by 4 under. So this is the answer of tan theta. Now this was the Olympiad problem, but from the concurrent theorem, it is one line numerical. So I may give you some question to practice on this theorem actually. But in JEE or any competition, the difficulty won't be this much, and therefore the basic torque method will give you the answer. But this is just for the idea. Like if you have something like this idea like this, it may help you solving some conceptual question easily. So if you see there are three forces, think about the concurrency. So first look for the forces whose directions are well known to us, and then try to make them concurrent, and you're done. Okay. So now let's do this question, one or two question. So this year ITJ problem came from my notes only, which I taught almost 9 years back. So they just picked the same question as the notes. So what was their question? So there is a rod which is again hinged. You know the concurrent theorem has not been used so far by JE, and that is why the possibility of using is very high. Because what I teach 10 years back is now they're asking. So hopefully, if I'm teaching you guys, it will come maybe next 5 to 6 years, and if you're lucky, then maybe next year.
So
But
this
I will
question
never
is
try.
also solved example in DC Pandey.
Yeah, maybe.
Yeah, it was a
This one,
3 mark.
which one?
This question was a 3 mark question, right?
The concurrency problem.
But this problem,
You're saying the
it was
concurrency on the concurrent problem.
okay.
Yeah. So concurrent problems are solved everywhere. It is not written, so they will never mention there is a theorem of concurrency. The concurrent theorem is studied in the BTech first year. So then now there is a rod and there is a wall, and there is a mass which is attached to the rod and passing through this. It is attached to here, and there is a block which we attach here. This is L length. So question is, what is the tension in the string? And here we have friction. There only it is fixed, else it will slip. So this point will have a friction, and that's why it will be wrong assumption to assume the same tension here and here. So this is the mistake that many students make. So you have to assume, let's say T dash. So now we know that T dash is mg. So T dash is known to us. The question is, what is T? Okay. So find the value of tension.
Yes.
This is very easy. This is just very easy problem, because what you are supposed to do is find the torque about the hinge and you're done. And because both the points are same, so the only if I make a mass of this as capital M, then things will change. So we have unknown force passing through the,
Sir, mg by sin theta.
yes. If I do not consider this mass, then your answer is correct. So assume the rod is massless, then what you said is correct. T sin theta equals to T dash. So let's make two cases. Case one, maybe let me remove this and this also. So this is Rx, this is Ry. Case one, if a rod is massless, then the only answer is very simple. The T sin theta into L equals to T dash into L. Luckily, both are at the same point. That's why L gets cancelled, and then you get T equals to T dash by sin theta, and T dash was known to us. So let's take case two. If mass of the rod is capital, then we have the torque question about the hinge only. So T sin theta into L, which was the case, will balance capital Mg into L by 2 plus T dash into L. Now the sin theta will come in the denominator. So T becomes Mg by 2, or in fact we can write like Mg plus and Mg by 2. Mg by 2 plus T dash, which is, what is T dash? Mg whole divided by sin theta. That's the only difference. So whenever you have a point of contact of a string with a body, and if it is given that the body is at rest, it means there must be some friction, and therefore the tension must vary on the two sides of the body. If you do not consider friction, then it will simply slip. So there is no question of equilibrium. So this is something like understood. So they do not mention, the difficulty here is they do not mention the friction value near the corner, but this is something which you need to assume on your own. All right.
Yes, sir.
So okay, let me give you some other question. I should have some question from. No, this is, look, I'll send you a PDF. Okay, so I've sent on a group. Here you may get the question of that nature. So you will get a lot of problem which requires this concept to solve. So if you want to solve, there are n problems. You can see there are some solved examples also. So no need to solve all question, but you must attempt some of the question. Okay. So the next concept is, which is very important. Again, this is not used very often. And this is called point of application. Point of application of force. So of forces. So we have many forces actually. So imagine a body is acted upon by a large number of forces. So it may be experiencing one force from this side, one from this side. So what we do next is we make a coordinate system. So we make a coordinate system, and these forces will produce some torque. So what we want to do is we want to choose a point at which, if the resultant of all such forces concentrated, then that must produce the same torque as these individual forces are actually created. Okay. So maybe the first force is here, second is acting here, third is so talk about O due to all force connect as a summation of Ri cross Fi. So let's say this brings some value to you. Now the point of application, let's call it P, is that point for which the resultant of all such forces creates the same torque as the sum of individual forces, which means if this is equals to R cross F net, then I can write better as Ri this R is called point of application. So very long time back, this was asked by JEE. Am I audible to you?
Yeah.
Yep.
Yes, sir.
So the point of application is that point about which the torque of a resultant force is equals to the actual torque due to all forces acting on the body. That's the only definition. We will not apply this force for in general case. We only apply for the parallel forces. So we apply this only for parallel forces. There are maybe one or two numerical or problem in you would have in the chapter of electromagnetic induction where you need to use this concept, else not used. So in your case, the question will be like this. So let's say we have a rod which is hinged at one end, and there are many forces acting at a different distance. One here, another here, maybe one here. This is F1, let's say this is F2, this is let's say F3. And the length we can say the gap as make it like this. One gap. So the full length is L. Yes, this is L by 2, L by 4. So now we can easily find the torque about O. So we want the point of application with respect to O actually. So first find the net torque due to each force. What we can write? F1 into L by 4 plus F2 into L by 2 plus F3 uh, into L. Correct? Now the net
Yes,
force,
sir.
if you add all force, it is 1 plus 2 plus 3. And let's say the resultant force we have to apply at X to balance it. So what is X here? X is F1 by 4 plus F2 by 2 plus F3 divided by this plus this plus this into L. And this is definitely going to be less than the L, and this is the answer. Understood? So this is the way of finding the point of application. So X is the distance. If you move X away, this is the point of application. Okay, all right. So the next concept is called problem based on toppling. So we need to topple somebody. So let's see. Let's see if I give you a rectangular body of a dimension. Let's say the L is the height. Maybe let's call it H and maybe base as B. This is the dimension of the body of mass capital M, and we are trying to topple it. So now, if you remember the toppling, when you topple something, you push it, and the bottom axis, the axis passing through the bottom, the axis passing through the bottom will try to topple the body. Okay, understood.
Yes, sir.
So first you try to understand that the nature of question that will be asked to you, how to imagine the situation and how to proceed. So generally what they will ask you that find the minimum force required to topple the body. So how much force you will apply that it will just topple, it will just fall down on the other side. That's the first question. Now the word is minimum force required to do so. Now every question of toppling is solved by assuming the system at equilibrium. So the way to approach such problem is imagine the system is at equilibrium. So you can always write the force relation and the torque relation and you can just make it a zero for a minimum force calculation. Well, so what does it mean is imagine you apply force and the body starts tilting. So the body will change the orientation. So you can see that when you apply force, the body will topple like this. Now try to understand the gravity acting on the body. It is always acting downward, correct? So earlier it was acting here, now it is acting here. So now you can see that the condition for toppling is if you apply a force which will tilt the body a bit. Now if you remove the force, it will fall back or fall forward. What will happen? If I, in this case, if I remove the force, what do you think? Will it fall forward or fall back?
Fall back.
Correct.
Fall back.
Now, exactly what is the condition to fall forward?
So the center of mass should be in the other direction of
Yeah. So the simple condition is
center
the
of mass should be
center
in
must
that direction,
must cross the vertical line. As long as the center mass is on this side of the vertical line, it will never fall forward, it will fall back. Okay. So let's take some other example. Let's draw the like tilted diagrams. So this is the process of toppling, which is happening here. And you can see the body is toppling about this point. So we'll try to understand the torque about O due to, I mean, in different situation. The minimum force criteria is fulfilled only when the torque applied by the force F is farthest from the center of mass and so from O as well. So the force must be somewhere here, right? So if you apply the force here, then it will have the maximum torque. Now, the question is the torque of gravity at this situation. So in the very beginning, what is the torque of gravity? If I say the base length is A, so what is the torque of gravity? Can you tell me the answer? Mg torque about O point in the very beginning.
mg/2.
Correct. Now, as the body will start toppling or tilting, not it has not toppled completely. If it starts toppling, the torque of gravity will be more or less.
Sir, less.
You all need
It's
to realize that as the toppling process will start, the gravitational torque will keep on decreasing or keep on increasing.
So keep on decreasing.
But what about the torque of force? Will it keep on decreasing or keep on increasing?
keep on increasing.
Yes,
You
so
can see it is going away. So the force is going away. But till this point, it will keep on increasing. So now something very interesting you need to argue that for toppling to begin, the force must create the torque more than torque of gravity in the very beginning, because once you create a torque more than torque of gravity in the very beginning, after that there is no need to think again, because we know that after that it is going to be always bigger than the torque of gravity. So if you overcome the initial torque of gravity, you will always be ahead of gravity, isn't it?
Yes,
So
sir.
the toppling is only possible if you in the very beginning make sure that the force is creating a torque which is slightly more than the torque of gravity, and that's done. Understood?
Yes,
So
sir.
for toppling to occur, the initial condition is only taken into consideration, not what happens afterwards. So the only diagram which will matter is the initial diagram, not what happens after. But we have to make sure that the body has been tilted by d theta. Now, what does it mean? So body looks almost touching the ground, but the reality should be, what is the reality?
it is
The
turned by
body,
elementary angle.
yeah, the body has tilted elementary value. So now you may ask why this elementary jump. So I'm just doing it slightly bigger for the clarity. So why this so? The answer is simple. Because once we assume the body has been slightly tilted, the normal will shift from the center to the edge of the body. So the normal will act here. And so the friction will act here. So now the friction and normal will arrive at the edge instead of the center or somewhere on the surface. And this is the force acting. So the force acting is here, the normal is acting here, and the gravity is here. And what I'm saying is every question of toppling, when we try to solve, the rule is simple. We assume the system to be in equilibrium, and therefore certain relation we can always write, like F equals to Fs and N equals to N. But this will never give you the condition for toppling. Why? Because condition for toppling requires that what is the condition, it will topple this side. So the more difficult part which you need to learn now is that gravity never turns a body. Gravity never topples anything. Now, although we calculate talk about bottom, because we are solving the question of equilibrium, so no matter which point you choose, you get the same answer. But let's talk about reality. Now gravity is something which never participate in rotational motion in reality. Although we make calculation and we do calculate the torque of gravity, but do not carry this in mind that gravity can turn something. Because if you carry this in mind, then we are making a big mistake. So I think we have discussed in some point back, some point like in some other lecture that gravity never creates torque, if you remember. And I had given you some example also. So gravity, okay, we calculate the torque of gravity as a mathematical value, but reality is gravity never calculate. I mean, never creates torque. It's like okay, I can give you example, but okay, I will not take it. Okay, so now now what is happening here? Now imagine the same analysis about center mass. Now once you think the center mass, the gravity will have zero torque. So torque about center mass due to gravity will be zero, right?
Yes,
And
sir.
you want to rotate like this. So when you try to push the body, try to see which one is helping and which one is opposing. So who will try to turn this way? Which force? F,
F.
yes.
Yes, sir.
But Fs is also doing the same thing. Fs is also trying to turn like this. See, about center of mass, the Fs, the friction force is also helping you, right? Isn't it?
Yes, sir.
So about center mass, F and about center mass Fs both are supporting your turning. Do you realize this?
Yes, sir.
Yes, sir.
Who is opposing here? Only normal. Because the normal is applying force here, which in turn is trying to turn like this. So Fs is trying to turn like this, F is trying to turn like this, and the normal is trying to turn like this. So the sum of these two torque is equal to this torque. Now to topple, this must exceed this value. That's the only reason. So numerically, because we are finding the minimum value, so we can just take equal value, equal sign. But the torque of applied force and friction, if it will exceed the normal torque, then, and we are doing this calculation about center mass, then body will topple. Now, as I said, we are always assuming the toppling as a equilibrium problem. So we can just write the value. We can just write equal sign. No need to think of this. So if we solve by assuming equal sign, and then we say that this should be slightly bigger. So it is equal on a bigger side. This is equal on a bigger side. This is called equal on a bigger side. This is symbol for that. This is on a bigger side. It is equal on a bigger side. Now, if you solve this way, or if you simply find the torque about O and 0, so method 1, this is also give the answer. This is reality. This is just a solution. Now, why I'm saying solution? Why not reality? The reason is gravity never turns something. In fact, it is the other force which turns the body around center mass. So this will lead to the erroneous assumption that gravity can turn something, because I don't want to create this perception that gravity turns. Rather, it is the other force which turns the body around the center mass. Now, both methods will give you the same answer, and why it will give you the same answer? Look at this. So let's do the question about the O point. About O, the good thing is the normal and friction will have no torque actually. So what is the answer? F into H minus mg
MGB by 2.
equals to 0. And so F is equals to mgb by 2. Okay. So this is a minimum value. So in general, the F should be more than F minimum to get the answer. That's it. So for minimum, we assume the equilibrium and we solve it, and then we say the F must be more than or equals to, or not equals to, slightly more than F minimum, which is, I mean, mgb by 2h. So this is how we solve. Okay. Now, if you solve by this method, it's not difficult because we can write torque of F is F into h by 2. So that's the distance from the center mass to F. And torque of friction is also Fs into h by 2, correct? And the normal is n into b by 2. And from the laws of motion, like equilibrium, translational equilibrium, we have got the answer. So you can see that the Fs is F and n is mg. So eventually it turns out to be same answer, correct? So you could solve the way you want. There are two possible ways to attempt a problem. Now, the first condition may think that okay, it is the gravity which is balancing out. So F is trying to topple and mg is trying to prevent. You can think that way. It's nothing wrong because we are solving the equilibrium problem about O, about the point about which the body is toppling. So whenever you're solving a question of toppling, we tilt mentally, we shift the forces near the edge because that is the only point of contact left, and then we write the equilibrium condition, and then we get the answer, whatever we are looking for. So now here the friction is sufficient, let's say, so we are not considering that the bottom is slipping. So what we are saying that friction is sufficient. I mean, it is sufficient to prevent the slipping. So we are assuming that the friction is sufficient to prevent but sometime our interest will change, and so the question of the examiner, so what they will ask to you that find the condition of mu s, the coefficient of static friction, such that body topples. The question is what is the minimum value? So body topples without slip. So I see if friction is infinite, then it will topple only. It will never slip. Now I am trying to put a condition that okay, let's not assume it's infinite friction. It is finite friction, but I want toppling without slipping. So what is the minimum mu s I should expect for which this will happen? So again, you will go back to the same problem. You will add the same condition of equilibrium. And now what you will do is the normal is acting here, we know. And the only difference is whenever they ask the mu is minimum, you need to make a small change. And what is the small change? If this is n, this becomes mu s n because it's limiting case. The rest is same. Your f is same, mg is same, and everything is same. Your condition is same. So you will write this is a, this is b, and I think you got the answer. So for top, you first solve that. You solve by putting the torque about O0, then you get the F into H equals to mg into b by 2. Don't think much, just solve it. Be calm and relax. Get the answer. You got the answer for F. Now think of the equilibrium condition. So this must be equals to
Maharashtra plus 9120.
so now we know this F is mg b by 2. Now what I'm saying is you just go ahead and write the equilibrium condition which is mu s into A. For minimum case we can just assume the limiting friction, that let's say this is the limiting friction which can prevent it, and therefore the n value we know is mg from again equilibrium, and if you solve you get a mu s minimum value directly, which is b by 2h. And what is interesting here, it has nothing to do with the mass. It depends on the shape of the body. If you have a rectangular body, then it is b by 2h. So toppling depends on dimension, of course the shape, and that is obvious that if you have a tall body, so you can see that if you have a really tall body, if h is large, the toppling is really easy, and therefore you can see that mu s minimum is also very less. You need a very small friction to topple a body. Another best example is a pencil. However flat a pencil may be, if you just keep on a surface, this pencil will topple with least friction. So even if you put on a tile, it will slip without toppling. Okay. So toppling demands some friction, and that we can easily calculate just by putting the limiting force, and we are done. Okay. So this is the one variety of question which has been asked by JE. Now mains has not asked so far, but hopefully mains may ask very soon. And these conditions are easily met. Now the third case that can ask is in this way. So by using the equilibrium, you got the F value, you got the mu s minimum value. Okay. So now we know that the mu must be more than mu s minimum to prevent slipping. Correct? So this is, if mu is more than this value, then the body will topple before or without slipping. So body can topple easily. So they will give you multiple choice question A, B, C, D, and in the options A, B, C, D, this options are X1 or not X1, so mu1, mu2, mu3, mu4. You have to pick up the option for which the body will topple without slipping. So you have to pick all options which is equals to more than this value. All values. So this becomes a multiple choice question, because every answer which is more than the minimum value is the right answer. Okay, so let's say this value turns out to be 0.2. So if the answer is 0.15, if B is 0.1, C is 0.2, and D is 0.25, then C and D are the right answer. So in this way, they may ask you the multiple choice question, or they may ask you which one of the following you see the incorrect value. Then A and B are the right answer. So these are the ways of asking questions in the examination. You need to be careful at how they ask, how they interpret the question, and accordingly you have to behave. Now this is the slightly difficult part for you, because this requires the complete knowledge of friction chapter. So depending on how much you remember. So in friction, if you remember, we had something called angle of repose, and this is the angle at which the body starts sliding on the surface, right? So you gradually increase the angle of inclination.
At mu is equal to tan theta.
Correct. So at angle where the tan theta is equal to mu, the body will start slipping. The moment this theta, so at theta equals to tan inverse mu s, or in fact you can say theta more than this angle, and we can take the limiting value. Body starts now in the chapter of laws of motion or friction, we used to discuss this for block, correct? And we used to assume that block is a point mass. And if it is a point mass, then it can only slip, it will never topple. So the toppling was totally ignored uh, in that chapter actually. Now, what if you try to take a plane and then instead of a small object, you put a big large object, maybe something like this. So you may put a cylinder, yeah, quite possible. And the cylinder will have some height h and a radius r. Now, what happens if I start tilting the plane slowly? It is quite possible that the body may topple before it will slip. So it is quite possible that if the angle at which the toppling occurs is less than tan inverse mu s, then toppling happens before slipping begins. Correct? But if the angle at which the body will topple is much bigger than the tan inverse mu s, what does it mean? The body will slip before the toppling will start. Now, how to find the angle of toppling? So it's very simple. Let's say you have already tilted this plane by value theta, and we are trying to find the condition for toppling. Okay, so let's draw the ability. So now this cylinder will look like this. I'm just doing the two-dimensional view. This is h, this is r, the half. So now because it's a body with uniform shape, the center mass is very much known to us, right? The center mass will be at h by 2, correct?
Yeah.
So here we are not trying to apply any force. Here now if the body will tilt, it will. I mean, if it will topple, it will topple about which point? The left axis, correct? So this is like O, and the friction will act Fs, and the normal will act like this. So these are the forces acting, normal and Fs. So instead of drawing the gravity like this, what I'll do, I'll draw the gravity as a component itself. And we know that this is the component called mg sine theta, and this is, so as I said, we always assume the equilibrium. So we take n equals to mg cos theta as usual, and mg sine theta equals to fs. And now we are trying to topple it. So for toppling, what we do is the torque about O, we just put it 0. That's it. Which gives a relation of toppling or condition of toppling. So about O, what is the torque of mg sin theta and mg cos theta? because that must be balanced. No? So mg sin theta will try to topple. You can think this way, and mg cos theta will try to prevent, isn't it? Mg cos theta will try to let it fall it back, but mg sin theta is trying to topple, and once the toppling will begin, it will never stop. So that's why the initial condition is sufficient to understand the answer. So what is the torque due to mg sin theta? Tell me.
mg sin theta h by 2.
Correct.
Yes, sir.
And this must be more than or equals to, basically we are solving the for minimum case. This must be equals to mg cos theta into how much? What is the torque of mg cos theta about O?
Mg cos theta r by 2.
R by 2.
R.
It is radius itself is half, na? R is a radius, not a diameter.
Yeah.
Yeah, sir, only R.
And now we are done because mg will cancel out anyway, and what we're getting is a dimensional relation. So tan theta turns out to be how much? R by 2h. So 2r by h.
2r by r.
Now h is anyway, h will always come in the denominator because the taller the body, easier the tilt, when easier the toppling, so smaller the angle. So it will topple very soon. The moment you lift the plane, it will topple if h is much bigger than r. So now we know the minimum angle of toppling. So theta minimum of toppling is tan inverse 2r by h, and we know the theta of slipping. So this is, if I call it, if I name it a theta t and theta s, which is tan inverse mu s, correct? Slipping. This is for slipping. So we have two angles. One is for the toppling angle, other is for the slipping angle. And what do you want? You want that the toppling should occur before slipping begins. Now, how to put into mathematical framework? So for toppling to occur before slipping begins,
So 2r by h should be less than mu s.
correct. So the theta of slipping must be bigger than theta of toppling. Like the smaller, the toppling angle should be smaller because I want this to occur first, right? And therefore, and tan is the increasing function, so we can say mu s is more than theta. If the coefficient of friction is exceeding the 2r by h, the body can topple before slipping can begin. And this is the toughest question for you from the torque concept. So here we are gradually increasing the angle of inclination of the plane slowly. Then two things can happen. You may see the body will uh, either slip first or topple first. And if you want, you can perform this with the example of you can take a small eraser and put on a scale and then tilt the scale. You can see what is happening first. If you want, you can see it. So mostly in case of eraser, the toppling will happen because it's having sufficient friction. And but if you change the orientation of the eraser, if you make it taller, you can see the toppling happens much before the shaping happens, and that you can do it easily using the eraser and a scale. So this is nice experiment you can perform, and you can check all condition what I'm saying. Okay, so probably you can do one or two more problems before we wrap up this topic, and this will come to culminate the chapter called torque. The torque is done. So let's do this question for a cone instead of a cylinder. So I want the same question, like condition for toppling to happen before the slipping begins. The height is h, and the radius is r. Question is find mu s minimum such that body topples before slipping begins. Assume theta is increased gradually. So we are changing the angle theta very slow. It means there is no acceleration kind of thing. It's happening slowly. So the equilibrium is maintained. Then the question is, what is the newest minimum so that the toppling will precede the slipping condition? Tell me.
So is it 4 by 3 into R by H?
4 by 3 into R by H. Why 4 by 3? What is the center mass of the solid cone from base?
H by 4.
H by 4. So the mg will act there, na?
Okay, I took actually took 3 by 4H. It is from the top.
mg, mg sin theta is like this, cos is like this, and the normal is like this, and friction like this. So the toppling happens about this point, correct? It will go on towards left, so we can just write mg sin theta into h by 4 is equals to mg cos theta into r. That's it. So we have the answer tan theta equals to 4 r by h. That's it. So the angle of toppling we got, and we know this they should be less than, or you can say mu is more than this angle, this value. If mu is more than this value, it will topple before slipping. So the mu s minimum is this much. That's it. So questions like this will come. I can just change the shape. I can make it a hollow cone, uh, some triangle, whatever. So yeah, we're done with the torque chapter completely exhaustively. We have done every question, every variety. So now we are good to enter the topic called angular momentum. But what I'm trying to this time make a change is, now I'm trying to bring the laws of motion first, and then I'll take this highly conceptual part called conservation of angular momentum and all in the last segment of this course. So now we'll start the laws of motion. Or we call it dynamics of a rigid body. Dynamics of a rigid body. So what are the steps to solve the numerical of RBD, the rigid body dynamics? Like what we need to think and how to solve it. So as I said, our syllabus is all about plane motion. So this is the underlying principle that for plane motion, the degree of freedom is 3. So you have 2 translational degree of freedom and 1 rotational. This is a very simple philosophy to solve. So just write net force along x equals to mass into acceleration of center of mass along x. That's simple. And the net force along y equals to mass into acceleration of center of mass into y. Done. And as a beginner, when you start solving numerical, I mean, don't think much. You just write things like this, and the next step is write the net torque about the z-axis equals to I center of mass about z-axis. Like the axis must pass through center of mass and must be parallel to the z-axis into alpha z, the angular acceleration. But these 3 equations will not be sufficient in all cases. So the fourth will be just like laws of motion. If you remember, the laws of motion not used to be sufficient. We used to bring the constraint relation. So similarly here we have the this plus constraint, and when constraint will come, when they will put the condition that there is no slipping. So when there is a pure rolling motion, the constraint will come. If there is not a pure rolling, if it is a slipping motion, then there is no constraint. So if there is no friction, I mean, if there is no constant, if there is no pure rolling condition, the 3 is sufficient. Okay. So if no pure rolling, then these 3 will be sufficient to solve the question, because the friction will be Fk, kinetic friction, whose formula is very much known to us. The moment pure rolling will come into picture, then we need this part and this part both together due to pure rolling. So you know how to correlate the alpha with ACM. We have done this part so far, and the problem is in pure rolling the friction will be static and there is no formula for it. So don't write any formula. So until it is not the limiting case, we cannot put mu s into it. This is not equals to mu s into it. This is only for limiting case. So as a beginner of this dynamics, how to solve a prolonged dynamics, the rules are simple. Just write the laws of motion the way you did in the first, I mean, second chapter of physics or third chapter. And the other part is torque equation. So write torque equation separately and then write net torque equals to I into alpha. Just like m into a will change into I into alpha. Now the y of this we'll discuss later on in after learning the angular momentum. And the reason why I'm bringing this before, so that you have the sufficient practice of writing the laws of motion, because by the time we'll finish the angular momentum, you may lose your energy or input to solve that. So many concepts will take away your energy. So now this is somewhat kind of cooler period. So we're trying to cool down the process, and then we'll again start doing those problems. Okay. So for this purpose, what I'll do is, yeah, I will have my Erodov. So we'll start solving from Erodov, all questions. So I'll just take Erodov and I will solve all questions one by one. Okay, so let me send the photographs. Okay, sufficient. So now these are problems which I have sent. No need to solve any of them. Just you can read later on. So let me start the question solving one by one. So we'll start with a very famous question that we also started in the chapter of laws of motion, and that was the question of at wood machine. Now, so when we were solving that chapter of at wood machine, if you remember, we assumed the pulley as massless, correct?
Yes, sir.
And now that is what we are going to change there. So now the pulley is not massless as it used to be. So now pulley is like a cylinder. It will have some mass. It will have some moment of inertia. It will have everything that we ignored earlier. So now this pulley is like full-fledged object now. So what you ignored earlier, you cannot ignore now. Okay, first. Second, again a rope will pass over the pulley, but this time there will be sufficient friction between the pulley and the rope to prevent any slipping. So now the constant is there. What is constant? There is no slipping between the pulley and the rope. So the constant part which they will mention directly or explicitly is there is sufficient friction to prevent slipping between rope and pulley. Now, they may not mention this way that there is sufficient friction to prevent slipping between the rope and the pulley. Rather, they will say there is no slipping at all. Now, it is up to you to infer that, okay, if there is no slipping, then that is only possible if there is some friction present. And now, the moment you assume the friction, which you never assumed earlier, the pulley is hinged at the center. So, the moment you assume friction, the tension will change on both sides of the pulley. If you remember, we have discussed this.
Yeah.
So this is, let's say, now these are blocks, these are same blocks. So here we need to realize that the M1, M2 will behave as they were behaving earlier. So they're just like point masses. The body is the pulley itself. So this pulley is like a body of radius r. You may think as a, I mean, sometimes they say that assume as a cylinder. So assume pulley as solid cylinder. Now, what does it mean? The moment of inertia will be known to you, and the pulley will turn about the central axis because that is it is hinged, so it can only turn this way or this way. I'm just taking this way, and because the pulley will turn this way, so the alpha will be this way. Alpha is the angular acceleration. Okay, anyway. So how to begin solving questions like this? So we always deal with the body separately. This is the body which we need to consider separately, and the parts are considered individual. So this question will have three parts. One, the laws of motion of a body called cylinder or pulley, and then the laws of motion of particle called blocks M1 and M2. Now, from the previous experience in the chapter of laws of motion, we know how to deal with these things. Now, because of the simple constant, if M2 will go down, M1 will go up, correct? And their constants are very simple. If M2 will go down with acceleration A, M1 will go up with acceleration A because it's the same string passing over the pulley, correct? So the A will be same. Understood? So these are the assumptions which you start with. So you know acceleration will be A and this and this. But what about tension? Will it be same or different? Tension force will be
different.
different. So if I say this as T2, if I say this as T1, the pulley will experience T2 and T1. You need not to get confused. You just write the laws of motion for each part separately, one by one. So let's begin with the pulley first. Now ask yourself, is pulley translating?
No, sir.
No. So it means there is no question of writing the translation equation. So therefore, you are free from writing these two equations. This is not required for the pulley. So we are done with the first two part. What is the third part? Torque equation about center mass. So can you tell me the torque of the T2 T1 about center mass? See, I would have drawn mg as well, but I know that mg cannot create torque about the center. So let's say this mass is m. So let's write the torque equation about hinge. So first write the torque and we can equate it with I into alpha, IC into alpha. So how we write this? What is torque about hinge? So if I assume that m2 is going down, it means T2 is bigger than T1, correct?
Yes, sir.
So what is the net torque about the center? It's T2R minus T1R, correct? So the T2 into R and T1 into R, the torque is, and why it is minus? Because T1 is trying to turn anti-clockwise and T2 is trying to turn clockwise, and I'm assuming that turning is clockwise. Okay, because I'm assuming M2 is going down. This is my assumption. You can assume other way around. It doesn't matter. Okay. So T2R minus T1R. So this is the net torque. Do we have any other force and any other torque? So we do have some other force like hinge reaction, which I haven't drawn. Ry. We have mg Ry, but we know that everything which will pass to the hinge will produce zero torque. So that's why I'm not writing. So this is the net torque, and this is equals to moment of inertia of a cylinder about the central axis size. How much? It is mi square by 2 into alpha. Alpha is the angular axis. So what we're getting answer is T2 minus T1 whole into R equals to mi square by 2 into alpha. And probably we can get alpha. So alpha into R equals to how much? Or you can say m by 2 into alpha. That's it. Now you may ask, sir, why you have written alpha together? Because now the time has for constant. What is the constant relation? The constant is this point is going down with what acceleration? Alpha, correct? Because this point will have the tangential acceleration alpha. And so the block M2 must go down with the same acceleration because the string is inextensible. So the two ends of the string must have same acceleration. That is what we know from constant. So if this point will go down with alpha, the every point below will go with same acceleration. So the block will go with same acceleration. So the constant relation is A equals to alpha. This is your constant. Or you can say no slipping condition will give you this answer. That every point will move with same acceleration A, and this is attached to this point of the pulley P. So the acceleration of the point P in the downward direction is the acceleration of the block. That's simple. And now we are done because I can just write as MA by 2 is T2 minus T1. So from the pulley itself, we got so many like this equation. But still, we have two more objects to deal with because their laws of motion must be written, which is m1 and m2. So what is the laws of motion for m1? Tell me what we can write. So these are just particles. So we just need to write the laws of motion.
Yes.
So for m1, it is t1 minus m1g,
T1 minus
G is M1A.
and for m2, it's again simple. m2g minus t2 is m2a,
M2.
and we can substitute t1 t2 from here. So we can take t1 from here, t2 from here, and we can put in the first equation. So using 1, 2, and 3, what we can add ma by 2 because we are trying to find a first. And what about t1? So t2 is how much? m2g minus a. All right, m2g minus a. And what about the t1? m1g plus a. And now you just need to rearrange the stuff. ma by 2 plus m2a plus m1a whole equals to m2 minus m1 into g. And the answer is simple. Answer is m2 minus m1 whole into g upon m1 plus m2 plus m by 2. And not a big difference from the previous answer. The mass of the pulley we have taken as m, and so the answer is m by 2 extra term. If I make the pulleys massless, you can see we are getting the same answer. So if pulley is massless, then tension will again become equal. Correct?
Yes, sir.
So from equation 1, you can say if m tends to 0, then T2 minus T1 equals to 0, which means T2 is equal to T1, the tension will be same. And therefore the pulley mass will not matter. So the answer will be same as the answer which we got in the laws of motion chapter. So the mass of the pulley brings some change to it, and the process of discussing or dealing is very simple. So we know the relationship between the A and the alpha. It's very easy. So every point which is connected to the like this pulley, we know its acceleration. So we look for the rope which is hanging from the block, and we can find the acceleration of that point, and that's how we can relate the values. So what you're supposed to do is you're supposed to don't look at the answer and attempt the same problem till you get some confidence. So I hope you know the answer, but this time I'm making a small change. So I'm not going to give you the mass of this pulley. So mass is not given to you for the obvious reason. Because now what I want is the radius is r, and the moment of inertia of the pulley is given I about center mass. So ICM is given as I. And now the same question. So I want to answer in terms of I and R instead of M. No need to put the I equals to MC MR square by 2 because that's not given to you. Only I is given. So same problem, no slipping condition, and you can choose the pulley to be going towards clockwise alpha, and then this will go down. This will go up, and then find the value of alpha and the acceleration of block. So if you find alpha, then finding the acceleration of block is easy. It's alpha into R only. Just solve this and tell me what is the answer to A. So tell me the A answer. That's it. And solve by thinking, not because I have solved, so you're trying to copy. Just think that why it was solved in that fashion. so that you can understand the way of thinking. Go ahead.
So is it M1 plus M, sorry, M2 minus M1G by M1
Mhm.
plus M2 by
Mhm.
M1 plus M2 plus I by R square?
Correct, correct. That is exactly the answer. The answer will be that only. Now you can open the question which I have sent, and from there go to the first page. Yeah, first page. So you can see there is a diagram 1.55. Okay, can you see that
Yes, sir.
1.55? Now that is the question number 1.243. Can you see that 1.243? It's above 1.243. Okay. Now instead of two masses, we have just only one mass which is wrapped over a thread on a pulley, and then you release the mass. Mass will go down, pulley will turn clockwise, and the same question. So can you solve now? Can you solve?
Yes, sir.
Okay. So attempt this question.
Yes, I got it, sir. Uh, small mg by small m plus m capital M by 2. A.
So I think that is the right answer. So anybody else who got the answer? Or Shita Tharva? Anybody?
So once
Yes, sir, on the last step.
I think this is given as small m, right? And this is given as capital M. And the radius is r.
Yes, sir.
Then the only tension is T, no? And the only torque will be T into R because the hinge is here. So T into R equals to I into alpha. The first equation is done. Now we can do it faster. And then we know that this will be A equals to alpha because this is the point which is being released by the pulley, and this point we know is going on with alpha as an acceleration. If alpha is the angular acceleration. Okay. And then the laws of motion for this block we will give you the rest answer. So mg minus t because this is equal to m into a, and then solving this two will give you the will give you the answer. Okay. So this is how you proceed solving the laws of motion. You begin with something very simple and then keep on doing the steps, and then the difficult part is the finding the constraint relation. And for pulley and thread problem, it's very easy. Just look at the point where the thread is released by the pulley and try to relate the values. So same question is 1.247. It's the same question. The pulley will turn, okay, and 1.5 it is slightly difficult because it's slipping is happening. So I think we should try the 1.58, and I think in fact we should try all questions. And in tutorial you can start solving questions. Okay. So I'm leaving all the questions for tutorial. Okay. All these questions, and I'll solve the double pulley problem which is below much below. So you can see that double pulley problems, and there is pulley with different radius. So those things will cover in the next lecture. So I will give you one complete lecture for the laws of motion part so that you can grasp a variety of questions. These are the small variety. I mean, then I'll give you some rigorous variety of questions which you need to know. And then in the other chapters, maybe after learning the angular momentum, I can give you some trick which can solve the question in one line. I mean, you can do these questions. Okay. So we'll see that. All right. And let me show you the trick part, like if just for one question. Trick. So if you take this as a system about O, look at the ABD. So mg is the only external force which can create the torque about the center, because and the torque is how much? Mg into R. That's it. And this torque equals to moment of inertia about the center, which will be basically mi square by 2 plus m r square. This is the answer. This you can do in one line, but before that we need to learn what goes inside this trick, and then it's easy. Same way you can do it. Same thing you can do it here also, like uh, m2 minus m1 into g into r equals to m2 r square m1 r square plus ICM into alpha. This is the one line answer. This you can do, but later. So there are a variety of things that we can do mentally, but that requires some other concept as well. But you do by the very basic method. So you attempt the fundamental way of solving the question. Tricks are there. I'll give you the tricks. Don't worry. So you will be master of all these questions, and probably you can do any question of dynamics of aerodynamically or in one line. You can see all questions in the book, and probably I can give you one line solution for every question. But that will never help you in the very beginning. So you need to first master the fundamental. Do it from the scratch. Once you are good with the scratch, then probably I'll give you the trick part, how to do this any question, almost mentally. Bye, guys.